All right, guys. So we'll get started here. um, so again, um, got to turn on the projector here. So just two reminders here will be homework 11 and homework 12. Okay. So homework 11 is due tomorrow and 12 is due on Monday. So they are both having extra credits. Okay. And then again, this Friday today, and then next Wednesday will be the makeup for if you have missing any labs before last week. Okay, that just last week was the last lab. So if you have anything missing, you can come in to make it up. Okay, either today or on Wednesday next week. All right, and then the current plan is still to have exam scheduled for Wednesday for the Wednesday lab attendees, and then Friday for the Friday lab attendees. Okay. And our course survey is still open. It will be closed by Wednesday. So make sure if you have time and make sure you finish the end of course survey. Okay. All right. So today we'll be looking at chapter 16 on oscillations or oscillatory motions, and put this away. Okay. And then we will briefly mention about waves, but most of the content related to waves we should discuss then next semester. Okay. All right. So first we'll be looking at this example. If you have a ruler, you can see if you hold one end stationary, and then if you pull the other end like slightly offside, if you release it, you will see that it go back and forth. Okay, so you'll be vibrating. So what happens here is initially the ruler is at equilibrium position. If you pull it to one side, then there's displacement over there. Okay, so if you pull it to the left hand side, the displacement is to the left, but then there will be a force that is making the ruler goes to the left, right. Okay, so on the other way. So the force as a result of the displacement, the force is in the opposite direction of the displacement. Okay, so that kind of force is called the restoring force. That means it has a tendency to pull the object back to its equilibrium point. Okay, and then when the ruler swings to the right, actually the force will be to the left. Okay, all right. Similarly, I think we had seen this before. So if you have a spring, if you pull the spring, so then there will be displacement to one direction, resulting force will be in the other direction. Okay, so that's also a restoring force. Okay, and for a spring, this is we know that it's governed by Hooke's law, which gives you F equal to minus Kx. Okay, most of the time we are just focusing on the magnitude, so F equal to Kx. But if you would look at the direction of the force, then force and x will be in opposite direction. Okay. All right. So those are two scenarios we can think about for a restoring force. Okay. Um, so let's take a quick look on the example of the Hooke's law here, just to get you guys familiar with, again, the spring constants and stuff here, okay? So this one says a spring has a length of 0.200 meters when a 0.300 kilogram mass hangs from it, and a length of 0.750 meters when a 1.95 kilogram mass hangs from it. What's the force constant of the spring, and then what's the unloaded length of the spring? Okay. Looks like I accidentally closed the slides. My touchpad is acting very funny today. All right. So on this one, let's see. So on this over here, you have a spring, okay, that hangs vertically. Okay, you have two masses, M1, and then another snail or the same spring over here, but now you have M2, okay, attached to it. That's assuming the unloaded length is somewhere here. So this is the unload length, okay? This is the original unloaded length. We can call it X0, okay? So then when you attach this guy over here, the M1, then the stretch is X1, okay? When you attach M2 to this guy, the stretch is as X2, okay? So you can actually write out two equations on this, okay? The first one will be, now on the masses here, this guy will be mg, right? M1g, and then the spring force will be kx1 upward. On this guy over here, you would have m2g, the spring force will be kx2, okay? So two equations you can write out, and then kx1 and m1g should be equal to each other, right? Because this mass is in equilibrium, okay? So you can basically write out that m1g equals to k x1. Or actually, I think it's referring to x1 as being the total length of the spring. Let me take a look here. All right. Yeah, so it says the spring has a length of that. It's not saying it has a stretch of that. So my label here is not correct. So this is x1. The total thing is x1 here. This is x2. Okay. All right. So then when you write out the equation x kx f equal to kx, this should be the stretch of the spring. That means you are referring to the original length x naught. Okay. So that's the first scenario. The second scenario, you can write m2g equals to k x2 minus x naught. Okay. So you have two equations here. You actually have two unknowns. Okay. So the first unknown will be the k. You're looking for k, and then the second unknown will be x naught. Okay. You are given m1, which is 0.3 kilogram. M2 is 1.95 kilogram. Okay. So those are knowns, and then it tells you the k is, or actually it didn't tell you the k. It tells you x1, x2. x1 equals to 0.200 meters. x2 equals to 0.750 meters. Okay. In these two equations, k is the unknown, x naught is the unknown. Okay. So solve for the two unknowns from two equations. Okay. So let's do this. We'll take the knowns into the equation here. So then it becomes 0.300 kg. The first equation times 9.8 meters per second square equals to k 0.200 minus x naught. Okay. The second equation, you'll be plugging 1.95 as m2, 9.80 meters per second square equals to k of 0.750 minus x naught. Okay. So then you can solve for both k and x naught. All right. On this one, on the left-hand side, this two multiply, it will give you 2.94. on the second equation, these two multiply each other will be 19.11. Okay, yeah, in newtons. Okay, so then basically, you can write one unknown as in terms of the other one. So say from here, you can write k equals to 2.94 divided by 0.2 minus x naught. Okay, and then replace k with this expression in the second equation. Then you'll be solving for x naught first, and then once you have x naught solved, you can have k solved. Okay, so this then the second equation will be 19.11 equals to k, which is 2.94 divided by 0.2 minus x naught, multiply 0.750 minus x naught. Okay, so what you can do is multiply both sides by this. So then this goes to the left-hand side. So 19.11 multiplied by 0.2 minus x naught equals to 2.94 multiplied by 0.75 minus x naught. Okay. And then you can solve for the x naught. Okay. Should be just a couple steps of algebra here. Okay. So I'm going to just tell you what's x naught. Okay. So a couple algebras there. So this give you x naught equal to 0.1 in meters. Okay. Once you have this x naught, you can put the x naught back into this the expression for k and then solve for your k. Okay. So then k equals to 2.94 divided by 0.2 minus 0.1. Okay. Which gives you k equals to 29.4. Should be in newtons per meter. Okay. All right. I'm going to pause for a few seconds to see if you guys have questions on this one. Okay. Just let me know. Point two. Which one for the no, yeah, I think it's it's 0.2. All right. All right. All right. And then just to recall that the energy for the spring so should be for the potential elastic potential energy should be 1/2 kx squared. Okay, x is the displacement with respect to the original equilibrium position. I think we learned this before. Okay, and then it could be also calculated by calculating the area underneath the curve, because the curve f versus displacement. Okay, the area underneath the curve will give you the work done. Okay, which is equal to the potential energy change. Okay. All right. So that was kind of review on the spring force or Hooke's law. Next, let's take a look if you have a mass being attached to a spring. Okay, so in this figure here, it shows like in a physics lab, you could have the air floated track. So then this thing is kind of floating on the air. All right, there will be air cushion between this mass and then the track. Okay, so then the friction is negligible in that case. If you pull the mass to one side from the equilibrium position, which is somewhere here. Okay, if you let it go, because of the restoring force, so then this will be pulled in that direction, and then when it passes through the equilibrium position over here, you're actually compressing the spring. So then there will be force pushing this mass to the right, okay? So the speed will decrease until it reaches 0. And then due to this force, it will start to move to the right, okay? And that will go back and forth, okay? So this is then a motion that repeats itself, okay? So such motion is called periodical motion or oscillation. And this is the simplest scenario you could have for an oscillation, okay? A point mass attached to a spring. And then the restoring force here is the F equal to, again, minus Kx, okay? So when you have a restoring force like that, you will likely have to have an oscillation or a periodical motion, okay? All right. So a few quantities we need to get familiar with first to describe an oscillation or a periodical motion. So first is the period, as defined as the time required for one cycle of the motion, okay? And frequency then will be the number of cycles of oscillations per unit time. That means 1 second divided by the period, okay? So, or 1 divided by the period. So that would be equal to the frequency. We use the F. The period is or the symbol for the period is the capital T. Okay, usually capital T means period and small f means frequency. Okay, they are inverse of each other. SI unit for frequency is in cycle, 1 cycle per second or 1/second or second inverse. You can it has its name also called hertz in symbol H, capital H, small z, hertz. Okay. All right. And also another quantity we want to know about an oscillation is called amplitude. Okay, so which means the maximum displacement you could have from the equilibrium point. Okay, so if you pull the mass to one end by the amount of A, then that will be its amplitude because it will not go to the other side that is exceeding minus A to the left. Okay, so this will be the maximum amplitude. Okay, if you pull to a particular location and then release it, then that will be your amplitude. Okay. All right, so that's the third quantity. Now, for the period, I think we actually took a look on an oscillation when we are doing simple pendulum lab. Okay, so we pull the pendulum to one side and then it goes back and forth. That's an oscillation or a periodical motion. So in that lab, we did the dimension analysis. That means we are looking for period, which is in second, and then we are looking at the quantities involved, and then we come up with an expression for the period. We can do the same here, right? For a point mass attached to a spring. So then the relevant quantity here will be the mass, the spring constant K, okay? And then you might be thinking about amplitude or the gravity here because we are on the surface of the Earth, okay? But let's take a look on the dimension for the mass and the spring force constant first. So for the mass, it has a unit of kilogram. For the force constant, it has a unit of newtons divided by meters, where newtons is equivalent to kilogram times meters per second. That's from Newton's second law. Force equals to mass times acceleration. Okay. So in that case, you can see then the force constant K should have a unit of equivalent to kilogram divided by second square, right? So then looking at these two quantities, the mass and force constant, you realize you could already be able to set up an equation that will give you the dimension just the second, right? Because you can do this divide by this guy, which gives you second square, and then you can take square root of it to get the second, right? So you divide mass by K, that gives you the units of second square, and then you can further take a square root of mass divided by k. That will give you the dimension you want in seconds, okay? Which is equal to t, and then again, t in this case will be proportional to square root of m over k, and the constant term of before this square root actually turns out to be 2 pi, okay? And then this is determined experimentally, all right? So then in this case, for a simple harmonic of a mass attached to a spring, the period is equal to 2 pi square root of m over k. So then the frequency will be 1 over t, which will be 1 over 2 pi, and then you flip m and k, so square root of k over m, okay? So this equation at the bottom gives you the frequency, and then the one above it is the period equation, okay? So this is the period. So you can see actually the period doesn't depend on the amplitude, okay? It doesn't depend also on g, okay? So it just depends on the mass and then the force constant. All right, let's take a look on this example here. It says a type of cuckoo clock keeps time by having a mass bouncing on a spring, usually something cute like a cherub in a chair. What force constant is needed to produce a period of 0.500 second for a 0.0150 kilogram mass? Okay, so for this one, you can just apply the equation for the period you learned from the previous slide. Okay, so T equals to 2 pi square root of m divided by k. Okay, you guys can actually have a quick check on this one by plugging the numbers into your calculator, okay, and then see what you get. Oh, actually, I think you use the equation t equals 2 pi square root of m over k, and you can rearrange the terms to solve for k here. All right, so this one, it tells us the period, which is the capital T, and then the mass. So you are looking for K, okay? So K is over here. You want to divide both sides by 2 pi first. So T divided by 2 pi equals to square root of M over K, okay? And then next you want to square both sides of the equation. So to get the K out of the square root, okay? So then you will have T square over 2 pi squared. That means 4 pi squared, right? Because you want to square 2 to get 4 and then pi as well. That equals to M over K, right? Now you're looking for K. You can do cross multiplication if you want. So then you get K T squared equals to 4 pi squared times M. So then K will be equal to divide both sides by T squared, okay? So 4 pi squared times the mass 0.0150, then divide by the T squared, 0.5 seconds squared, okay? So this will give you 2.37 newtons per meter, okay? All right. Okay. So if you guys are clear with that, we can move on. Yes. So if you rearrange the terms, you should get what's shown on the screen over here. So K should be equal to M times 4 pi squared divided by T squared. Yeah, and then there's a question in the chat asking about what's the unit. I think I didn't write clear. It's newtons over meters. Okay, so the K should be in newtons over meters. Okay. All right. All right. So for simple harmonics motions, so actually the car you are driving has springs. Okay. Between the axials of the tires and the main body. So then if you look carefully, if you are driving through a bumpy road, actually the body of the car is going up and down, right? Or if you look at the headlights, if you are driving in the night, then you'll see the headlight actually goes up and down there. It looks like a wave you would have in like water in a pond or in ocean. So in that case, you can see there's link between simple harmonic motion and then waves. Okay, so because they have the same pattern over there. All right, and then actually this can be demonstrated in lab. So if you have a mass attached to a spring, if you pull the spring to a certain stretch and then release it, and it will go back and forth. Now, if you put a conductive paper underneath it and then roll it with a certain speed, okay, then you'll see the motion of the mass as being as like kind of wave on the paper here, okay. So for a wave, it can be either described by a sine or cosine function, okay. So fundamentally, a sine or a cosine function, they are actually the same. If you look at sine function and then the cosine function, if you put them in the same graph, you can see they are pretty much the same, except they are shifted by a certain angle, right? So then you can use either sine function or cosine function to describe a wave or a single harmonic motion. Okay, so in this textbook, it uses cosine function. If you are reading another textbook, you might find that it's using a sine function. Okay, but they are the same. Okay, so just keep in mind they are the same. Just preference of the author. Some really, I think most people prefer cosine. Okay, sometimes people prefer sine, but they are the same. Okay, so you can write a cosine function to describe the position of the simple harmonic oscillator or the point mass. So then it's equal to the amplitude times cosine of, in the parenthesis here, you have 2 pi divided by the period, okay, times time t, because the position should be a function of time t, small t. So small t is the variable time, capital T is the period of the motion, okay. And then you can see that if this small t is increased by a capital T, then it actually repeats itself, okay. Because then in that sense, in the parenthesis, you will have 2 pi over t times small t plus 2 pi if you add capital T to the small t, okay? So then it actually repeats itself, okay? A cosine function, 2 pi apart, basically repeats itself, okay? All right, now let's take a look. If you use a cosine function, that means you pull the point mass to the maximum first and then let it go. So then you will, the displacement will be decreasing first and then reaching the equilibrium point, right? And then increase in the opposite direction and then decrease and then reach the equilibrium point, etc. Okay, so this is a cosine function. Now, if you look at for the velocity of the point mass, you'll be doing the slope of this cosine function, right? So the slope over here, it should start with, because you are at maximum. So the slope at the maximum should be 0, all right? And then you are going down, so that means it will be increasing in the negative direction. So then the velocity, if you look at the plot of velocity versus time t, you'll start from 0 and then increasing in the negative direction, reaches the maximum when it's at the equilibrium point, okay? So at the equilibrium point, the point mass will have the maximum velocity, okay? And then decrease and then reaches 0 when the displacement is at the maximum, okay? So you can see this then will be a sine function, but a negative sine function, because this goes into the negative, okay? For a sine function, it goes up here, all right, in the positive direction, but this is a negative sign, okay? And if you want to look for the oscillation, so when we describe a motion arm object, we are interested in its position, its velocity, and its oscillation, right? Just as what we did for the linear motion. So then oscillation here, then you'll be looking at the slope of this velocity versus time t curve, okay? So at this point, you can see the velocity, the slope at this point should be maximum, right? So that means your oscillation start as maximum, but this is in the slope over here should be in this direction, right? So it's decreasing direction. So then your oscillation should start at maximum of negative number and then increase, okay? So this is something like a cosine function, but negative or cosine function, right? If you compare to the cosine function over here, it should start at the maximum positive, but oscillation start as maximum negative. So that means this is a negative cosine function, okay? So the position is a cosine function, then the velocity should be a negative sine function. The oscillation will be a negative cosine function. Okay, so this is what you would expect for a simple harmonic motion. And we call those equations as equation of motions for simple harmonic motion. Okay, so x equals to a maximum value times cosine of 2 pi t, capital T times small t. Then velocity is a maximum, negative maximum sign of that function, okay? And then it turned out that this maximum value for the velocity is equal to the acceleration times square root of k over m. Okay. And then similarly, it can be derived that the acceleration is equal to minus k times a divided by m, and then cosine function. Okay, cosine of 2 pi over t. All right. So those are the velocity and then acceleration equation of motion for a simple harmonic motion. Okay. So you can see if you know amplitude and if you know period, actually period is in terms of m and k. So basically you can, if you have 3 parameters here, the amplitude, the k, the mass, then you will have the equation of motions, okay, for the object, for the point mass. All right, now let's take a look on here. This example says a 0.454 kilogram block is attached to a horizontal spring that is at its equilibrium length, and the force constant is 24.0 newtons per meter. So the block rests on a frictionless surface. It says a 0.0454 kilogram watt of putty is thrown horizontally at the block, hitting it with a speed of 8.80 meters per second and sticking. How much time does it take for the block or system to come to rest? First time right after the impact. So we can make a sketch here and then visualize the problem. Let's block initially attached to a spring at its equilibrium position. Okay, so this is x equal to 0, the equilibrium position. Now you are throwing a small, we can call this as capital M, the larger mass. You are throwing a small body. You can call it m, small m, with an initial velocity of 8.8 meters per second. Okay, and then it will stick onto the large block. All right. So they will stick together, compressing this guy. With this one on this side over here. So when you are at here, you will compress the system to when it's coming to a rest. Okay, so V equal to 0. It's asking you how much time is this? How much time does it take? So the knowns are capital M is 0.454 kilogram, small m is 0.0454 kilogram. The V0 is 8.8 meters per second. And then the spring constant is 24.0 newtons per meter. Okay. So I think traditionally it would probably like solve for the V here at this point. So let's call this V final, okay? So you probably solve for the V initial, right? You can actually do that because this is a collision. You can apply momentum conservation over here. So the small m V0 should be equal to, after the collision, you combine the two times this V, right? You can solve for that. And then, but then the problem is when this guy is being moving, it's moving to the right over here with the velocity, right? This is a varying velocity. And then the oscillation over here is also varying. Okay. So you then wouldn't be using the equation of motions, right? Because for the one-dimensional equation of motion is assuming A is equal to constant. Then this time, this is not constant, okay? So then you probably wouldn't be able to figure out the time t using the approach there, okay? However, since we learned the simple harmonic motion this time, right? So for a simple harmonic motion, it goes like cosine function, right? So over here, now you can see actually we are looking for the time when it's hit it after the collision. This system would have a maximum velocity, right? It's at the equilibrium position over here. So this is a V versus T curve in this scenario, okay? It's actually a cosine function, okay? So then it reaches at 0 here when it's going here, right? And then you can imagine it will go there and then come back, reaches to another velocity at 0 and then go back, right? So this will be oscillation motion going back and forth, right? Now the time it takes from here to here, it will be 1/4 of the total period t, right? Because when it goes here, this is 1/4 of it and then comes back, this is half. Now another quarter and then goes back, right? So this is the total time period. So then this time is equal to 1/4 of the period you have for this oscillation motion, right? So if we can solve for the period for the oscillation, then we can solve for the time t it takes. Okay. So now, because this is a simple harmonic motion, which tells you t is equal to 2 pi square root of m over k, right? And when we check on this equation, we just have one mass, right? Now we have two masses together, so you can just simply add them up, okay? So small m plus capital M on the top there. That will just then give you, because then you treat them as one system, you just need to add the mass up, okay? The two masses up, all right? So then the T that is being asked will be 1/4 of this 2 pi square root of small m plus capital M divided by k, okay? That will give you pi over 2. This and this will cancel out. Partially the 4 becomes 2. Okay, so pi over 2 square root of m. The two add up. Okay. Now I can just plug in the numbers here. Pi over 2 square root of 0.05 or 454 kilogram plus 0.454 kilogram divided by 24.0 newtons per meter. Okay. So that will give you the time it takes. And then it turns out to be 0.227 seconds, okay? All right, so you can see it doesn't matter what the initial speed of the party is, okay? So 8.80 or whatever, maybe 100 meters per second, you'll still get that because the period or the time required is not related to the velocity, okay? It's just determined by the mass and then the spring constant. Okay. All right, I'm going to again pause for a few seconds to see if you guys have any questions on this one. All right, if not, then we can check on the next section here quickly. We have about 10 minutes left. I think that should be enough. All right, so the next will be the simple pendulum. So we know it's an oscillation motion. It's a periodical motion. It repeats itself from the lab we did, lab 7, and then also from lab 8. Okay. So basically, if you look at the free body diagram of a simple pendulum, if you pull it to one side, okay, so then you can see there's weight, there's tension. You can resolve the weight in the direction that is along the stream direction and then perpendicular to it. Okay, so in this direction, the component of weight will cancel out the t. Okay, then this will be the remaining component, that will be the net force on this guy. Okay, so you can see again here, if you pull it to one side, then the net force is this component. It's in the opposite direction of the displacement, right? This is equilibrium position. Displacement is in this direction, and then the net force is in the opposite direction. So then this component of the weight will be the restoring force for this system. Okay, so then you will go back and forth and back and forth. Okay, that's the driving force there, or the restoring force required for the oscillation here. Okay. So if we write the net force over here, F is equal to minus mg sine of theta. Okay. Now, if the angle is not too large, okay, so then the sine of theta is approximately equal to theta. Okay. If we want to use small angle approximation, this is called small angle approximation, then this theta should be in radians. Okay. I think let me just show you this first, the small angle approximation first before we actually look at the equation. Okay, so if you have an angle, you can put the angle here. This is in degrees, and then you can convert it into radians over here. So basically, you are just typing the equation, say this is equal to radians of this guy, then you'll convert the angles from degrees to radians. Okay, and then you can do sine of it. Okay, so sine of the angle, so it will be sine of this guy. In Excel, when you do sine or cosine function, your angle should be in radians. Okay, just keep that in mind. It's not in degrees because you want to use the SI unit there. So you can see if you increase the angles, you can see the angle and the theta and sine theta, they are pretty much equal to each other, right? Angle in radians is pretty much equal to the angle in the sine theta, right? Until we reach to about 15 degree, then it starts to have some deviation. Still quite close, okay? But the deviation start to show up over here, okay? Sine theta versus theta is a linear, pretty much the early part over there, and then kind of curve up, okay? So if you go to about, say, 20 degrees, then this is about 1% of difference, okay, for the theta and sine theta, okay? If you can look closely over here, 0.349, this is 0.342. Or actually, it's close to, it's about 3% difference now, okay? So as long as your angle is less than 15 degrees, so this is less than, this is about 1% difference, okay? These two are about 1% difference. As long as your angle is not greater than 15 degrees, then you should expect small angle approximation to be very accurate, okay? So let's go back to the PowerPoint slide over here. Go back. All right, so you can write F equal to minus mg sine theta, which you take theta, sine theta as theta, okay? So then the length, arc length over here, if you pull it by a small distance s over there, that should be equal to L times the angle. Okay, that should be in radians. So that's called arc length there. Okay, so theta then is equal to S divided by L. Okay, you can replace theta with this expression. Now, if we want to be aligned with the expression we have for Hooke's law, which equal to F equal to minus Kx, then we replace S as X. Okay, that's the displacement. So then the force here, net force here equal to minus mg over L times the X, the displacement. So the mass and g, they are constants. If your bulb is chosen, then mass is constant, right? L is constant. It doesn't depend on the x, the variable, how far you are pulling it to the equilibrium point, okay? So those are all constant. They should give you a constant number, right? So then F is equal to minus a constant number times Kx times Sx, which is exactly the same format as the Hooke's law here when you have a mass attached to a spring, right? So F equal to minus Kx, okay? In the case of the pendulum, you simply replace K with mg over L, okay? So then the net force is in the same expression, okay? So then you should expect also the oscillation motion there. So for the period of a simple harmonic of the simple pendulum, then you replace K. So this is the period for a mass attached to a spring, okay? T equals 2 pi square root of m over K. Now for a simple pendulum, you replace K with mg over L. So then you arrive at 2 pi square root of L over G, okay? So this is the period for a simple pendulum. And that's what we also studied in the lab, okay? All right, so in the lab, you probably have seen this. If your angle is less than 15 degree, your percent difference is actually should be less than 3% or 1%, okay? And then as the angle goes up, then you see deviation to start to increase, okay? In some cases, you may see 5%, okay? All right. So then let's take a look on this one here. A quick example here. It says, some people think a pendulum with a period of 1 second can be driven with mental energy or psychokinetic, kinetically because its period is the same as an average heartbeat. True or not? What's the length of such a pendulum? Okay, so simply on this one, you will just use the equation for the period equation for the simple harmonic motion, the pendulum. Okay. So T equals to 2 pi square root of L over G. It gives you T as 1 second. You're looking for L. Okay. So again, simply similar to what we did for the second example of the day. So you divide both sides by 2 pi, and then that equals to square root of L over G. Then you want to square both sides of the equation to get L out of the square root. Okay. So then you will have T squared over 4 pi squares equals to L over G. Okay. So then L is equal to, you multiply both sides by G. L is equal to G times T squared over 4 pi squared. Okay. Then you can just plug in the numbers there, 9.80 meters per second square times T squared, 1.00 second over 4 pi squared. Okay. That will give you the length about 0.248 meters, right? So if you remember in the lab, when we did the first trial, we say take a length about 0.25 centimeter, which is close to this one. And then the period was pretty much like 1 second, right? You probably got like 0.99, whatever. So it's this guy here, okay? All right, I think that would be it for today's lecture. So for Monday's lecture, I think there's just a couple short sections remaining. So what I'm going to do is I'm going to just record the lecture. So it should be a very short, maybe 20, 30 minutes video, and then you guys can watch it on Monday, okay? Just by yourself, okay? All right, so that would do it for today, okay? Now, in the scenario, if there's any change about the plans for the final, you'll get email from me, okay, about that. But otherwise, we'll stick with the original plan, okay?